In this video I will show how to use the Airspy HF Plus as a power meter. I have 3 of them here, as you can see, and I will compare them. The starting point is what I find on the internet about the Airspy on the home page of Airspy. Go down a little bit here. And here I can find the specifications. It says minus 140.0 dBm at 500 Hz bandwidth in HF. Well, that was at 15 megahertz, and I don't think it differs very much at other frequencies within the HF band. If the unit is modified, of course, on the input with this R3 capacitor, if you want to do measurements at the low end of the HF spectrum at long waves. I'm running the latest SDR Sharp by April 25, 2018. And this is the version 1.0.0.1666. And the firmware for the HF Plus is 1.7.0, although these things don't matter much, because I'm looking for properties of the hardware. I have switched off the HF AGC and on the preamp and no attenuation. With these settings I expect the noise figure to be as specified for the unit. I have set a bandwidth of 500 Hz and a very high order, and this is to have the appropriate bandwidth of 500 Hz well defined, and I will verify that by switching on a signal generator. And you can see it is here at the edge on one side, and I can step it in steps of 10 Hertz. And you see the level is the same, it's flat. But if I go 10 Hertz outside, we don't hear it anymore. I have to increase the amplitude by, this is 10 dB. 20 dB, so about 15 dB. So it falls off within about 10 Hertz, and that means an uncertainty of perhaps 20 Hertz as compared to 500 Hertz, and the associated error is then negligible. Nothing to worry about. I have connected a 50 ohm dummy load instead of the signal generator or an antenna or something. And now I should read minus 140 dBm. So I enable the signal diagnostics here and wait. Maybe I should press rebuild. And this is a funny integrator that converges fairly fast initially and then gradually slower and slower. So I wait for a while to get a good accuracy on this measurement. And it looks stable now, so I press acquire. Now when it collects this noise, it will get 0, because it subtracts from this reference level. It means that 0 is minus 140 dBm. If I would inject from the signal generator minus 140 dBm, I would read here 3 dB, because signal and noise would be equally strong, so they would sum up to twice as much, which is 3 dB. I will not send 140 minus dBm, but minus 120 because I don't trust the precision of this generator to be isolated well enough to give 140 with some precision. So I should read now 20 dB on this meter, and I press the rebuild to have it start properly, and then I wait. And you can see the error is 1.6 dB. That's a pretty good precision. So I can measure the absolute power to within 1.6 dB, but I don't know whether the error is due to this instrument. It's specified to plus minus 1 dB, if I remember correctly. So I will do some extra testing. I have now connected another generator, and it has been acquiring for a time, and I read 21.7 dB. So it seems the generators are very similar. And I try a third one here. And press rebuild again. And it's about 0.2 dB stronger. So it seems this HF Plus unit is about 1.5 dB more sensitive than it is supposed to be. Now I have connected a different Airspy HF Plus unit with the dummy load on the input. I have not acquired the new noise level. It is about 1.7 dB lower, so the gain is lower in this unit. And I store this, and then I rebuild to make sure I didn't make any mistake. And I wait for it to see that it converges to 0. And this is accurate enough. So I connect the minus 120 dB signal and press rebuild. And as you can see, the error is now, when we use this as a power meter, the error is now 2.7 dB. That's a fairly good precision, although maybe a little bit less than one would really want. And of course this means that the noise figure of this unit is a little bit better than specified. 2.6 dB better. I will check the third unit, and this has 0.4 dB more gain than the second unit. I mean, I'm here with the dummy load. So I will acquire this and connect the signal generator and wait for a while. I have pressed rebuild and now waited for a while, and you can see this unit is also about 2.6 dB more sensitive than specified. So I have checked the 0 point. Now I will look for linearity, means I will increase the signal level here by 10 dB and rebuild. And now I expect 32.6 or something. And the precision I have here is much better than the precision I have on this instrument. Because this is an analog attenuator which has some error, although this is math inside the PC. And as long as the AGC or something is not switching in, and the analog parts don't saturate, this is going to be very accurate. So I continue upwards, 10, 20 dB more, and you see, well, I press the rebuild to make it faster. We are now 50 decibels above the calibration at 140, minus 140, this is 50 decibels up, and I read 52.9, means probably I detected an error of 0.3 dB in the signal generator. I will try another one. Rebuild. Well, 2.6 dB was the calibration error. I mean, how much better than specified the noise figure is on this unit. And the thing is, when the signal here reaches 0, measurements are no longer valid, because then there is a digital AGC switching in. But I can add 30 decibels more, means minus 60. And then I should expect 80 decibels here. And of course, I should expect 82.6, which is what I get. And now we are so close to this full scale, so measurements should probably not be done above this level. But I can measure powers from minus 140 dBm up to minus 60 dBm with an accuracy within about 3 dB or so, just on the specification of the radio and with a dummy load. Now at minus 60 dBm, I can look for the signal on the spectrum analyzer. I couldn't see it when it was very weak. But here I can see it is about 0.4 dB stronger than it should be. And that doesn't really mean anything, because the precision of anything is specified plus minus 1 dB. I have now put the dummy load back and showed the alternative to use Linearity instead for this kind of measurement. I have set the bandwidth to 1 kilohertz. You can see that if I shift the frequency a little bit. 7.4 and then 8.4, and it's fairly precisely what I want. At this point in this box, feed in whatever number required for the dBm meter to show minus 140 dBm. Sorry, I made it a 1 kilohertz bandwidth, so I should show minus 137. Means 51.7 instead. And if I read it out, I see minus 137.0. I could have changed the bandwidth and waited for a while, but this is equivalent. Now I switch on the generator here. Sorry, I have to connect it. I see on the S-meter graph is minus 117.9. That's an error of 2.1 dB. And I think for this particular unit it agrees pretty well with what I saw with the SDR Sharp. So I go up here by minus 60, for example, and I have to shift the scale here a bit. Here. And I run it a little bit faster. And I can look for the level. Minus 57.7. That's an error of 2.3 dB. And in the same direction, of course. And in Linearity, I look for the amplitude margin by pressing A. And it's 30 dB. So I think it will be okay to increase the signal level. We will see. 10 dB. And this looks like 10 dB. .6. That is an error of 2.4, 2.35. 10 dB more. And I didn't get 10 dB anymore. Something is nonlinear. So I look at the amplitude margin and it's still 15 dB, but the digital AGC of the HF Plus has done something. So what I read is minus 40, and that is actually the level I have, but I should have had the error still. So something is not okay. And then 10 dB more. And the signal level looks like it is lower because there is digital AGC destroying this type of measurement. But we can do measurements from the noise floor up to pretty strong signals with very good precision using these units and without the need of having a signal generator that is well calibrated. The error is only a couple of dB. This unit has now been running for about 1 hour, so it is now normal operating temperature. The previous tests were with cold units, but now it is maybe 40 degrees centigrade or something. This thermometer actually suggests 32.8, and that is on a black painted surface, which looks brighter than the surrounding metal, but it says 32.0 on the enclosure. And you can see here, it depends on how the light is reflected. So not 40, but maybe 33 degrees, while the room temperature is 25. So it's almost 10 degrees warmer than before. I have had it accumulating now for a long time, and it shows 0 to within a few hundredths of a dB. And I will collect a minus 100 dB signal from this generator. And now the rebuild button was pressed about 30 seconds ago, and I have a perfectly stable value, which is correct to within 0.7 decibels, well within the specification of the signal generator. So there is a fairly high precision in this type of measurement if you wait for the unit to be warm. Now, this was on 15 megahertz. I will check some other frequencies. This is 25 megahertz, and I have been running for more than 30 seconds. And the noise level is about 5 dB lower, so I acquire this level and then inject minus 100 dBm here. The level converges much faster than in 30 seconds. I read now 40.53 dB. That's a half dB from the desired, the correct value. I mean, I am 40 dB above the MDS as was specified on 15, but it's the same on 25. Again, the dummy load, but now on 5 megahertz. The level here is much higher than it was on 25, so I click on acquire and then connect the minus 100 dBm signal. And click on rebuild. And you can see it converges fairly rapidly. I don't have to wait 30 seconds, a bit less. Here, the calibration error doing it this way is 1.2 decibels. So the noise figure or sensitivity or minimum discernible signal is about 0.75 dB better than it is on the 15 or 25 megahertz frequencies. And now the dummy again on 2 megahertz. And that has been running for quite some time, and I can see the noise floor is 0.45 dB or 0.46 maybe above what I found on 5 megahertz. So I press acquire here and then connect the minus 100 dBm signal. And it stabilizes at 40.98, 1 dB above the nominal signal level. So the sensitivity is fairly flat over the HF range from 2 megahertz up to 25, probably also 30, although I didn't check that. The dummy load again, and now I am on 1 megahertz. And I have waited long enough. So I will connect the signal generator. And I still read 40.8 dBm above the minus 140 reference point. So also at 1 megahertz the precision is still pretty good. The dummy load again, now at 300 kilohertz, and after quite some time I read 1 dB more noise than I had at 1 megahertz, so I store this and then connect the minus 100 dBm signal. And after a while it stabilizes at 40.05. It means the sensitivity is now a little bit less, by, was it half a dB or something? But the precision using this method for calibration is still very good. It's actually better here than on the higher frequencies, where the unit is a little bit better than specified. Now, I have only tested this on one of the units after having it running for long enough time. The enclosure is about 10 degrees warmer, but components inside are probably significantly much warmer than they are on the cold unit or a unit that has been running only for a couple of minutes. Now the dummy load again, but this time the frequency is 100 kilohertz, and I read the noise floor 2 decibels higher again and store that, and I will connect the minus 100 dBm signal from the signal generator. Now this is very ugly. I don't know if the noise floor was affected by the connection of the signal generator. I will switch it off, and you can see I have to click rebuild. And the noise floor is about 2 dB higher than it before, so this broadband noise extends into the channel where I do the measurement. This is not acceptable. Normally you would think this is USB noise, but what it is something I think rather unexpected, and I will show that. I have put the dummy load back, and now it's clean again. And then I hold the cable from the signal generator onto the metal of the dummy load. And this is what I see. Then I hold it onto the outer part of this adapter, like that. And this is something similar, a little bit better. Next step, I hold it on the nut of the SMA connector, here. And it's very small. And I hold it on this other, means connect to the box, and there is nothing. And of course, if I connect to the box here, I would expect nothing, but I do see a little. Means maybe I should tighten this nut a little bit better that holds the SMA connector. So now on the nut here again, and then I disconnect, and I see nothing now. But of course, on the adapter, I still have this problem. Now I connected a different adapter and do the same again. And I see a very small effect. So this one is much better. And I was on the dummy load, so I go on the adapter instead here. And here the interference is very small. I should clean all the surfaces carefully with isopropanol or something. Maybe that would help, but for what I'm doing now, it's not necessary to go to the extreme. And now I connected the signal generator, and there is too much noise now. And it is switched off. If I disconnect it and hold the screen there, I don't have this noise. So it's from the inside of the generator. So I put the 20 dB attenuator here to hopefully get it 20 dB stronger, which I didn't. I cannot explain this at the moment. Well, it was not difficult. Now with the attenuator, if I connect it like that, I have all the problems. So the ground connections on this attenuator, or the attenuator itself, it's not RF tight. I will try to find something better. This is another 20 dB attenuator. Sometime I found it 19.13, so probably not so exact in attenuation. I still have this interference, but it's significantly lower, maybe by 20 dB even. So I switch on the signal generator and make it 80 or maybe 79, sorry, minus 79 dBm, and press rebuild. And sensitivity is something like half a dB lower, but we still have a good precision using this as a power meter with a dynamic range of, was it 260 dB or something? Well, you can see earlier in this video at what point it starts to not work properly anymore. We are 40 dB up now, and there is 10, 20, 30, 40 dB up to the top of the dB scale. So it's about 80 decibels of dynamic range, and that is in a bandwidth of 500 Hertz. We can do measurements of sine waves at much narrower bandwidth to see much weaker signals. So we have something that can compare with pretty good spectrum analyzers. Maybe not in precision, and it's a little bit more complicated to use it this way because you have to calibrate for each frequency when you want to measure it, and you have thermal stability problems. The unit has to be warm enough. But I think it's interesting.